What if I told you that the answer to one of the biggest problems in modern tech, our computers literally overheating, isn't buried in some high-tech lab, but is actually swimming around in the coldest water on Earth? Seriously. Today, we're going to unravel how a bizarre biological mystery holds the key to the future of AI and even saving human lives.
Okay, so our story starts in, without a doubt, the most hostile marine environment on this planet, the Antarctic Ocean. We're talking about a place where the water is so unbelievably cold it should be deadly to pretty much any fish. And yet, life is thriving there.
And right away, you hit this massive paradox. I mean, how on earth does a living, breathing creature with blood and tissue just casually swim around in water that is actively trying to turn it into a solid block of ice? When you look at the basic laws of biology, it shouldn't be possible.
Let's just put some numbers on this because they're pretty wild. The ocean itself is almost 2 degrees Celsius below freezing. But a normal fish, its blood freezes solid at around -1. So for this specific fish, the nautothenioid, even the tiniest touch from a stray ice crystal should kick off a fatal chain reaction. It's basically living on a biological knife's edge every second of every day.
So, the secret to this incredible survival trick isn't some kind of magic. It's a masterpiece of molecular engineering, something that's been perfected over millions and millions of years. This is where we dive into the science of how this fish literally built its own personal molecular shield against the cold.
And you know, this isn't some recent adaptation. We have to go back in time, way back. Around 30 million years ago, as Antarctica started to freeze over, a group of fish faced a really simple choice: evolve or go extinct. Their answer was to develop these incredible little molecules called antifreeze glycoproteins, or AFGPs. And this trick was so successful that today, these fish absolutely dominate the Southern Ocean.
The secret weapon here has a pretty technical name. It's called thermal hysteresis, but the idea is actually pretty simple. Think about it. Normally, water freezes and melts at the exact same temperature, right? 0 degrees Celsius. But these proteins, they create a buffer. They push the freezing point way down, maybe to -2 degrees, but the melting point stays up at 0. That 2-degree gap, that's the fish's survival zone.
And this right here, this is the molecule that makes it all happen. It's the hero of our story. Yeah, it looks super complex, because it is, and its very specific, intricate shape is the entire key to how it works. It's what allows it to grab onto ice in a way that almost nothing else can.
So how does it actually pull this off? Well, imagine a tiny, microscopic ice crystal getting into the fish's bloodstream. Before that crystal can grow and start doing real damage, these antifreeze proteins just swarm it. They physically latch onto its surface, and once they're on, they are not letting go. They basically form a protective shield, completely blocking other water molecules from joining in and making the ice crystal bigger. They don't melt the ice, they just stop it dead in its tracks.
Okay, now I want you to completely forget the freezing Antarctic for a minute. Let's make a hard pivot and jump to a totally different world. A world that is getting dangerously hot every single second. I'm talking about the world of artificial intelligence and the massive data centers that power it all.
40%. Just let that number hang there for a second. This is not some small, manageable issue. This is a massive, energy-devouring crisis that is seriously threatening to put the brakes on our most advanced technology.
Right, so that 40%, that's the chunk of a data center's entire energy consumption that's used for just one thing: keeping the hardware from literally melting. See, powerful AI chips get so incredibly hot that our old-school method, just blowing air across them, is basically like trying to put out a bonfire with a desk fan. We're hitting a thermal brick wall.
The only real path forward is to switch from air to liquid. And the difference is it's staggering. Liquids can absorb thousands of times more heat than air. Making this switch isn't just a minor upgrade, it's an absolute necessity. It can slash cooling energy by up to 90%, and it is completely essential for the future of AI.
But there's a catch. Liquid cooling has its own problem, especially if you want to push the limits and run systems at super chilled, sub-zero temperatures for peak performance. What do you do if your coolant freezes? And this right here is where our two stories, the Antarctic fish and the AI supercomputer, suddenly and beautifully collide.
This quote from Forbes just nails it. It perfectly captures this huge mental shift that's happening right now. We're starting to realize we need to think about our technology less like static machines and more like dynamic, almost living systems. And in a living system, you don't solve problems with brute force, you solve them with biological elegance.
And here it is, the hidden truth, the direct parallel. The fish needed to stop ice crystals from growing in its blood. Our AI systems need to stop ice crystals from growing in their liquid coolant. It is the exact same problem. And nature already solved it for us 30 million years ago. So now engineers are creating synthetic molecules that perfectly mimic the fish's proteins to make coolants that simply refuse to freeze.
But the impact of this incredible discovery, it doesn't just stop with supercomputers. This same technology, inspired by a fish, is on the verge of revolutionizing a field where every single second is the difference between life and death: modern medicine, specifically organ transplants.
You can just see the difference. It's night and day. Right now, a donated organ is only viable for a few precious hours when it's stored on ice. But by using these antifreeze principles to supercool an organ, chilling it way below freezing without letting ice form, we could extend that window from a handful of hours to several days. This is an absolute game changer.
And the science behind it is exactly the same. The number one enemy of a preserved organ is the formation of sharp little ice crystals that basically shred the cells apart. By adding molecules that act just like the fish's antifreeze proteins, we can stop that damage from ever happening, which allows for much colder and therefore much longer preservation times.
And listen, this is not some far-off sci-fi concept. This is happening right now. Companies like Xtherma are actively developing this tech, and they say it right on their website. Their inspiration comes directly from those Arctic fish, using that same bind and block mechanism to control ice and save lives.
So when you put it all together, what does it really mean? I think we're seeing this profound, fundamental shift in how we solve our biggest engineering challenges. We're looking less to mechanics and more to biology. For me, this is the most incredible part of the whole story. We built these godlike artificial intelligences, we reached for the stars, only to find out that the solution to one of their most basic physical problems was hiding in the veins of a fish, in the bottom of the world, the whole time.
And that really points to a wilder future, doesn't it? It suggests we're learning to integrate the very logic of life itself into the things we create. We're moving away from a world of rigid, breakable hardware and towards a future of fluid, adaptive, bio-integrated systems.
It really leaves you with one last huge question to think about. If the answer to supercomputing's heat crisis was in a fish, what other impossibly complex problems that we're facing today has nature already solved, just waiting for us to finally pay attention?
Don't go anywhere, hit subscribe, and we continue.
You know, when we think about the next big tech revolution, we usually picture sterile labs and silicon wafers. But what if I told you it's actually coming from the deepest, darkest parts of our oceans? It turns out nature has been perfecting technologies that we are only just beginning to wrap our heads around.
It sounds like the start of a bad joke, doesn't it? But the answer here isn't a punchline. It's actually the key to a future where we don't build our technology, we grow it. Okay, let's dive right into this.
So our story starts with this little creature, the crystal jellyfish, Aquiora victoria. For decades, scientists were just captivated by its strange, eerie green glow. They had to know, what was the secret behind its light? Turns out, the secret is this incredible little molecule called green fluorescent protein, or GFP for short. You can think of it like a tiny biological machine. It soaks up one color of light, blue, and just spits it back out as a brilliant green. It's nature's own super efficient light bulb. And believe me, it is about to change, well, pretty much everything. So what is it about this one protein that has bioengineers so excited? Well, unlike a lot of other fluorescent molecules, this thing is completely self-sufficient. I mean, its ability to make light, it's baked right into its own structure. You don't need any other fancy enzymes or anything. You just need the single gene for it, pop that into a cell, and that cell can start cranking it out. It's stable, it's crazy efficient. We're talking an almost 80% fluorescence quantum yield. It's basically plug and play for geneticists, a total game changer. All right, so you've got this incredible biological tool, and naturally, a few really clever scientists started thinking, okay, what can we really do with this? I mean, lasers are usually made of things like crystals or gases, right? But what if you could make one out of life itself?
Now, to really get how wild this is, let's do a super quick refresher on how any laser works. You just need 3 basic things. 1, a gain medium. That's the stuff that actually amplifies the light. 2, an optical cavity. Think of that as a couple of mirrors that bounce the light back and forth. And 3, a pump energy source to kick the whole thing off.
And this right here is where we get to the big breakthrough. Back in 2011, researchers at Harvard and MGH asked a question that honestly sounded like it was straight out of science fiction. They asked, what if they could replace that crystal, that gain medium, with a single living cell packed with that amazing jellyfish protein?
The setup itself was just beautiful in its simplicity. They took a single human kidney cell and they genetically programmed it to produce massive amounts of GFP. Then they sandwiched it between 2 absolutely tiny mirrors. I'm talking a gap of only 20 millionths of a meter, barely wider than the cell itself. And then they zapped it with a tiny pulse of blue light.
And what happened next was astonishing. The cell didn't just glow. No, it lit up with a focused, coherent beam of pure laser light. And here's the kicker. The cell wasn't just a passive container. Its own round shape acted like a natural lens, focusing the light and actually making the laser more efficient. The cell itself was part of the machine.
But here's the part that really changes everything. The detail that made this truly revolutionary. The cell survived. It wasn't destroyed in the process. It was still alive, and it could keep on firing laser pulses over and over again. They had created the world's very first living laser, a piece of biological hardware that could literally self-heal.
Okay, so this is that moment. This is when a really cool, fascinating experiment starts to look like the beginning of a massive technological revolution. We're stepping out of the realm of pure biology and into photonics, the science of light. This is where that humble little jellyfish protein starts to change our entire world.
You see, creating a living laser isn't just a neat party trick. It's the proof of concept. It's the blueprint that shows us that biological materials can be seamlessly, perfectly integrated with our most advanced technologies. Just think about the computers we use every single day. They all run on electrons, right? Shuffling through silicon chips, but that process generates a ton of heat. And honestly, we're bumping up against the absolute physical limits of how small and fast we can make them. But computing with light, with photons, is a whole different ballgame. It's way faster, it's incredibly energy efficient, and as we just saw, the components could literally be grown in a lab. And that brings us to this truly mind-bending new frontier, biocomputing. We're talking about a whole new paradigm where we perform computational tasks not with silicon chips, but with molecules, with proteins, with living cells. The advantages here are just staggering. Seriously, we're talking about hardware that uses a tiny fraction of the energy. Hardware that's completely biocompatible and even bioabsorbable. And maybe the wildest part? It can be self-healing. Imagine an implant inside you that doesn't need a battery and, when its job is done, your body just reabsorbs it, gone. So where does this hit the ground first? Medicine, for sure. You could use these biolasers to detect individual cancer cells with incredible precision because the light they emit would actually change based on their internal structure. Or we could activate light-sensitive drugs exactly where they're needed and nowhere else. This is real-time biosensing from inside your own body.
But, with any technology this powerful, this world-changing, creating it is only the first step. The next step, and honestly maybe the harder one, is figuring out how we're going to use it wisely.
This brings us to a whole new set of challenges, and there's an acronym for it. GELSI. It stands for the governance, ethical, legal, and social implications. Because, let's face it, when our computers are literally alive and our data can replicate itself, yeah, our old rulebook just doesn't apply anymore. This tech forces us to ask some really profound, really difficult questions. Like, what about scalability? If we build massive computer systems out of bacteria, what happens if they get out into the wild? And data storage. If your personal medical data is stored in cells that can divide, who owns that information? And what about errors? What's an acceptable error rate for a biological computer that's diagnosing a disease? These aren't just technical problems, they are deeply ethical ones. I think some researchers summarized it perfectly. We are entering a world where the lines we've always drawn between machines and living things, between information and biology, are starting to completely dissolve. So, the jellyfish gave us the key. Human ingenuity built the very first living laser. But what comes next? That's on all of us.
As we stand here, right on the brink of this incredible biological revolution, the single most important question we have to answer is this: what are the rules for computing with life itself?
Don't go anywhere, hit subscribe, and we continue.
You know, in nature's grand design, some of the most advanced tech is just hiding in plain sight. Take the lotus leaf. It grows in some of the muddiest water you can imagine, but it stays perfectly, almost impossibly clean. This isn't just a plant, it's a self-cleaning machine, perfected over millions of years. And here's what most people don't realize: we're only now just beginning to crack its code. Just watch this. Water doesn't stick to the lotus, it practically recoils from it. It forms these perfect little jewel-like spheres that just seem to hover on the surface. And as they roll off, they become these tiny microscopic janitors, pulling every single speck of dust and grime along for the ride. What's left behind? A flawless, clean slate. It's literally nature's original self-cleaning technology.
And this, of course, raises a really tantalizing question. What if we could actually reverse engineer this ancient secret? What if we could steal nature's code and, etch it into the very fabric of our modern world?
Okay, so to really get this, we have to go way beyond what our eyes can see. We're about to peel back the layers on this amazing biological marvel and uncover the intricate mechanics that make this whole self-cleaning miracle even possible. Let's zoom in.
For literally thousands of years, the lotus was a symbol of purity, but nobody really knew why. Its true secret was locked away. That mystery lasted all the way up until the 1970s, when the first scanning electron microscopes gave us our first real glimpse into its hidden world. But the final piece of the puzzle? That didn't snap into place until 1997, when a botanist named Dr. Wilhelm Bartholdt finally decoded the surface and gave a name to this incredible phenomenon: the Lotus Effect.
So what did those powerful microscopes actually show us? Well, the answer isn't on the surface, but in the surface. We're now going all the way down to the nanoscale to see the tiny, intricate blueprint that nature engineered for perfect cleanliness. Okay, this is really the core of the whole discovery. On a typical smooth surface, like say glass, a water droplet just collapses. It spreads out to maximize contact, right? It wets the surface. But on a lotus-like surface, the water does something completely different. It basically levitates, balancing itself delicately on the peaks of the structure, defying gravity and just refusing to spread out. And this is that structure. It's a brilliant two-level architecture. First, you've got this microscopic mountain range of bumps, each one just 5 to 10 micrometers high. But here's the really critical detail. Each one of those tiny mountains is itself covered in a forest of even tinier, waxy, nanoscale crystals. It's this texture on top of a texture, this two-tiered roughness, that changes absolutely everything. So this structure creates this fascinating physical state. Scientists call it the Cassie-Baxter state. The best way to think about it is like a bed of nails for the water droplet. The droplet's own surface tension keeps it from collapsing onto all those sharp points. Instead, it just hovers, supported by a cushion of trapped air. And the result of all this? The water is barely even touching the leaf. We're talking only 2 to 3% of the droplet surface actually makes any contact at all.
There's a name for this extreme water repellency: superhydrophobicity. It's the perfect marriage of physical structure and chemical properties. The geometry creates that air cushion, and then the waxy chemistry gives it that final push away. It's this elegant two-part system that unlocks the power of self-cleaning.
Okay, so we've decoded nature's blueprint. We get the science. And this is where things get really, really interesting. What if we could take this organic code and etch it permanently into the hardest materials we know? What if we could actually teach steel to behave like a leaf?
And listen, we're not talking about some temporary coating or a wax that's just going to wear off over time. We're talking about permanently changing the material itself. Using these ultra-fast, high-intensity lasers, scientists are now able to carve this natural, self-cleaning code directly into the surface of metal.
The results are, well, they're stunning. On the left, you're seeing the pattern nature evolved over millions of years. And on the right, that's a metal surface after being hit by a femtosecond laser. It's not just an approximation, it's a near-perfect copy of that crucial dual-scale roughness. This is biomimicry at a level of precision we have never seen before. The process itself is surprisingly elegant. First, they scan the natural blueprint of the lotus leaf.
Then they program this incredibly fast laser. It's called a femtosecond laser, and it fires pulses that last for just a quadrillionth of a second. This intense energy doesn't just cut the metal, it actually causes the surface to self-organize into the exact micro and nanostructures they need. They call these patterns laser-induced periodic surface structures, or LIPS. It's a one-step, totally chemical-free way to permanently rewrite the rules of a material's surface. So, we've taught metal to clean itself. This is way more than a scientific curiosity. It's a breakthrough that could reshape entire industries. Let's zoom back out for a minute and explore what a truly superhydrophobic world might look like. Let's start with a problem that affects millions of people. In the US, it's estimated that 1 in every 25 hospital patients will get an infection during their stay. A huge number of these are passed on from the very surfaces that are supposed to help them heal. Bed rails, IV poles, and doorknobs. This is where this tech becomes a real game changer. See, those microscopic ridges don't just repel water. They create a surface where bacteria just can't get a foothold, which could lead to chemical-free antimicrobial surfaces in hospitals. On ship hulls, it stops the buildup of marine life, a super costly problem called biofouling. For airplanes and infrastructure, it means anti-icing abilities. For any metal out in the elements, it's powerful anti-corrosion. Even our green energy gets a boost, with self-cleaning solar panels that stay at peak efficiency. Let's just focus on one of those for a second: global shipping. Biofouling, all that stuff growing on a ship's hull, creates a huge amount of drag, forcing the engines to burn way more fuel. By using a super hydrophobic, anti-fouling surface, the industry could cut its yearly fuel consumption by almost 10%. The savings, both in money and in carbon emissions, would be absolutely astronomical. Which brings us to a pretty remarkable conclusion. We are right on the cusp of a revolution in materials science, and it's all being guided by blueprints that are millions of years old. The future, as it turns out, is ancient. The real takeaway here is a big shift in perspective. Nature isn't just something to be preserved. It's the world's most advanced research and development lab. It's been running trillions of experiments for billions of years, perfecting solutions to problems we're just now starting to figure out. The blueprints are all around us, just waiting to be read. The Lotus Effect is just one chapter in this enormous library of natural innovation. From the iridescent scales of a butterfly's wing to the sticky feet of a gecko, the world is just filled with these elegant solutions. And it leaves us with a final, really profound question. What other natural blueprints are out there, hiding in plain sight, just waiting for us to look close enough?
Thanks for exploring the wonders of nature with us. If you enjoyed this journey, support BioVellum by liking, subscribing, and sharing. Let's explore the secrets of nature together.